Good morning, good afternoon, good evening to all of you, wherever you're joining from. Today, I'm going to make a presentation on compute governance. Before making the presentation, I'd like to thank the organizers of this unconference for organizing this. This is not only an amazing conference, but this is quite timely because all of us know everywhere now it's after the Korean summit, there's been a lot of talk about AI safety, which obviously is very important now. And I also would like to thank the participants and the people involved in the unconference. And as far as my presentation is concerned, I'm going to make it into three parts. First is compute. What is compute? A basic high-level overview of what is compute. And secondly, why compute? And third, how we can govern compute. This is basically a policy-specific presentation. So I'm giving a high level overview because in order to make effective policy, we need to understand the technology. If we don't understand the technology, we won't be able to make effective policies, right? And second, I'm not getting into the technical details of whatever hardware, software I talk about because I know the audience out here is mixed. Some of them are quite experienced, some are beginners. So I try to make it as general as possible. So with this, let's begin with our presentation. Now, the title of the presentation, as you can see, is about compute governance as a policy lever for effective AI governance. Now, all of us know that AI governance is picking up. It's picking up steam of late. The reason being, uh, some of the all of us know some of the models have been known for creating risks. So we need to govern the AI systems in such a manner that we can mitigate the risks. Now, before going into policy making, we need to understand what compute is. See, you can make policy with respect to data, algorithms, or compute. Here, I'm talking about compute. Now, when we say compute, what do you mean by compute? Okay, basically the term is used in two ways. One is the number of computations needed to perform a particular task, such as training an AI model, which basically is measured in flops, floating point operations per second. So that basically talks about the calculation, the kind of matrix multiplication which takes place in a model. Okay, number one. Number two, compute is used to refer to hardware like chips, like GPUs. People talk about GPUs nowadays. It's the talk of the town, right? So that is also one way in which the word compute is meant. Now, I'd like to refer to the definition of OECD. OECD, this definition is very important. It says AI computing resource or AI compute includes one or more stacks of hardware and software. See, AI compute is not a single thing. It is a layer. It's a stack of hardware, software, and infrastructure. Okay, we cannot limit it to one thing, right? And what it says is stacks of hardware and software used to support specialized AI workloads. These are like not simple kind of compute we need to run our laptops or any other machine we have. But these are specialized AI workloads because it involves deep learning, right? So what it does is this compute helps in running all these applications in an efficient manner. Now I'll go into the details of what these layers are. Okay. The first, if we break up the definition of OECD, what do we get? We get, as I said before, AI compute includes both software, hardware, and infrastructure. Okay, these workloads, AI workloads, are not performed by one hardware or software component, but by stacks, which are layers of components. The stacks include storage, memory, networking infrastructure, etc. Okay, and these are designed to support AI-specific workloads and applications which run matrix multiplication and process data at scale. Sorry. Now, in order for AI training workload to be successful, it is very important to have an efficient interaction between hardware and software, which I'll talk about in my later slides. Okay, next, AI compute stacks are specialized. These are specialized. For example, one specialized AI compute we can talk about is the GPUs, the chips. These chips are different from the normal CPUs, which do sequential processing, but this GPUs do parallel processing. It has got cores. Cores divide the problems into separate parts, and the processing takes place in multiple ways. So this parallelized processing, because vast amounts of data needs to be processed when it comes to deep learning, right? So this is not possible with the normal run-of-the-mill CPU. So GPUs are the thing, and it makes the entire process very efficient. So the compute infrastructure is very specialized. Now, going to the next slide, see, compute requirements can vary significantly. It depends on who's the developer. Okay, so depending on the application, AI system life cycle, for example, you need more compute. The compute requirements are different for training, for inference, size of the system. So it can vary. Okay, so compute requirements can be provided by your huge hyperscale clusters, cloud computing providers, or there are small the requirements for a guy, a lone developer can be very small. Okay, so compute requirements vary according to the national AI strategies of different countries also. Now, AI compute supports AI workloads and application. I've already talked about it. It supports applications in an efficient manner. So now let's talk a bit about the hardware layer. Now, as far as we have seen that when we talk about compute, there are three layers, three stacks: hardware, software, and infrastructure. Now, let's get a high-level overview of hardware layer. Now, the first thing when you talk about hardware, the first thing that comes to the mind for most of us is chips, definitely GPUs. So these were all of us know, originally designed for image processing and computer graphics application. And it began to be used you can say the deep learning era started around 2010, 11, 12. That's the period when the deep learning era started. And Andrew Yang was the first to use GPUs for deep learning. It was probably way back in 2008. So mostly it began to be used, GPUs for deep learning in around 2012. And why GPUs? It's because of the fact that, as I said before, parallel computation. Okay, so as I've already discussed what parallel computation is, so that was the major advantage of GPUs over CPUs. And this parallel computing can also be enhanced by connecting multiple AI chips together. Okay, and these GPUs are mostly used in training, and it is used in inference also, but primarily it has been used in training. Okay, so after GPUs, another kind of chip is FPGAs, field programmable gate array. Now, what this chip is something which can be customized. You can customize it. It can be reprogrammed to desired functionality after manufacturing. Okay, so you can easily customize it, and it is commonly used in applications where flexibility, speed, etc. is important, and it's generally used for inference. Now, another kind of chip is ASICs. ASICs are application-specific integrated circuits, and all of us know about Bitcoin mining and the kind of chips used there, mostly ASICs, and they're designed for it. If you are looking for a specific chip for a specific application, then ASIC are the chips. Okay. One example, a good example of ASIC would be the TPUs developed by Google. The tensor processing units are generally categorized as ASICs. Okay. Now, but this is very important, and some of the components of a compute hardware, if you see, is logic, memory, and interconnect. Now, logic is the place where all the computations take place, all the processing takes place, all the calculations, mathematical linear algebra calculations take place. And it is measured in floating point operations per second. Okay. Now, whatever operations have taken place, whatever is the output is stored in the memory. Okay. Now, what connects this logic and the memory? It's the interconnect. So once the computations are done in the logic, then through interconnect, it is again stored in memory. Okay. Then after hardware, as I said, there are three layers, and it's important from the perspective of policy to know a high-level overview of this three layer. So we have done one layer, which is hardware. Now I'm coming to the second layer, which is software. Now, see, if we have the hardware, but if you don't have all the three all the three layers have to work together. It's not like you can use software or hardware infra and you can do magic with your data or algorithm. Now we have the hardware, but what is the software? It is the bridge that connects the developer to the hardware. You want to maximize your output from your hardware, then you need the software. Now, for example, 2007, NVIDIA launched CUDA, Compute Certified Device Architecture. So that is a language, that is a platform which helps you to access the GPUs. right? So it acts as a bridge that allows users to develop applications by utilizing the capability provided by hardware. Okay, it is then you have the PyTorch and the TensorFlow. Okay, so what all this does is enables users to communicate instructions that are then executed by hardware. So without software, you won't be able to get access to the hardware. You can't use the hardware, leverage the power of the hardware. Okay, so that's the software layer. Now, after the software layer, we have the infrastructure layer. So till now, we have finished two layers. As we know, when we talk about AI compute, OECD definition says generally what it means is hardware, software, and infra. We've done hardware, software, now infra. Now, infrastructure layer is all about cloud, data centers, okay, and the ancillary resources needed for data centers, like for functioning of data centers, you need servers, cables, cooling equipment, etc. So that's the infrastructure layer. Now, I'd like to talk about three types of data center infrastructure here. Now, one is the computing infrastructure. What does it contain? It contains servers. We know in the data center, there are racks, there are servers. Servers contain GPUs, right? So then there are memories, chips, then there's the storage infrastructure, then you have the routers, cables. So all these comprise the infrastructure layer of the compute. So in a compute, we have the hardware, the software, and the infrastructure. All three have to work together if you want to leverage the power of AI compute. Okay. Now, this is, as I said in the beginning, if you want to make policy which is effective, which is proactive, evidentiary, anticipatory, then you'll have to know the technology, at least a high level overview of technology. Now, I have completed my first part, which is about compute. What is compute? Now, I'm going to talk about why compute. Why is compute important? Okay. Because, see, we have data, we have algorithms, we have compute, right? Now, I'm leaving aside data and algorithms. I'm talking about compute and why compute is important because it's the new oil. We have been hearing for the past so many years, data is the new oil, data is the new oil. But what is the entire narrative is changing now. Now, what is happening is now compute is the new oil. It is a valuable resource, right? I'll come to the fact why it is important in my couple of slides later on. All of us know there is a massive demand for compute. Okay, there is so much demand for GPUs, right? We have been reading in news every day. The demand is so much, the GPU companies like NVIDIA, AMD, Intel are finding it difficult to supply the kind of GPUs that are in demand. And compute is very scarce. You can't get compute if you, if you want compute, you can't go and get it because it's very difficult to access it. But the only few players, mostly the compute cloud providers, hyperscalers, they have compute. So along with data and algorithm, it is vital element for the development of AI systems. Okay. Now I'd like to this quote from this is something which Elon Musk said last year. I just brought it in. So that was the time when everyone was talking about GPUs, and he said GPUs are at this point considerably harder to get than drugs. Okay. Now, we know compute is important. Now, what's driving? We have seen in the previous slide that there is a huge demand for compute. It's scarce. Now, we got to know what's driving the exponential growth in demand for compute. Okay. See, it provides the necessary infrastructure for, as I said in the beginning, you have data, you have huge amounts of data. Where do you process it? Right? You need compute to process it. Right? You have algorithms, you have very complicated algorithms. You got to run them. Where are you going to run? You need compute for that, right? So it enables machine learning models to learn from patterns. Okay. So what is driving the exponential growth? Because compute has because what happens if you talk about scaling laws, right? You scale compute, you'll come up with models which are capable. Some models have come out which are very capable, and they have achieved that capability by scaling compute. Okay. So the more capable models, what happens? More risk. Okay. So then again, the AI safety issue. The compute used to train notable machine learning systems, if you connect with the previous slide, has doubled roughly every 6 months on average and growing by a factor of 350 million over the last 13 years. So you can just imagine. In 6 months, it has been doubling. If you look at the graph, now, compute use for AI training runs. This is basically the period 2010, deep learning era starts. Training compute doubling times 6 months. Okay, this is from 1950. This is the release date of the models when it was released. You can see starting from LXNet somewhere around 2008-9, GPT-1, AlphaGo, mixture of experts, AlphaFo, GPT-2, Gero, DALE, GPT-3, everything, all the big models are here. Gemini. So what does Gemini use? It uses something very close to 10 to the power 26. Okay. Now, this is the beginning of the deep learning era, 2010. So it doubles every 6 months. Okay. Now the next slide is also the same thing, but it talks about release date 2010. These are the flops. This is 10 to the power 15. Where is it? Petaflop, exaflop. Okay. If you see here, for example, if you take GPT-2 out here, right, 2019, then you can see. So it doubles every 6 months. Okay. Now compute costs. Compute costs are very high, so everyone can't afford it. Okay, because on an average, large-scale AI models use about 100 times more compute than other AI models. Okay, and it's and there's data which says that if model sizes continue growing along the current trajectory, some estimates place compute costs in excess of entire US GDP by 2037. Okay, so the costs are high. Okay, massive cost when it comes to compute. For instance, training GPT-4 costs more than 100 million. Okay, so now this slide is very important. Now, in order to make policy, because this entire presentation is focused on policy, how do you make effective policy? We have to know the entire semiconductor supply chain. Okay, it is said that a semiconductor, a chip travels around 25,000 kilometers before reaching the endpoint. So last year, probably trillions of chips were manufactured. It crosses about the borders of 70 countries from its origin till the end. I'm sorry. Okay. Now let's look at the semiconductor supply chain. For example, NVIDIA. Let's take the example of NVIDIA. NVIDIA is one of the, it designs chips. It is a fabless company. Fabless means it does not fabricate or manufacture chips. It designs chips. And it uses a software called EDA, Electronic Design Automation. It designs chips, and it controls around 80 to 95, 80, almost around 75 to 85% of the market, design market. So once the chip is designed, it has to be, say for example, NVIDIA, because it is a fabless company, fabrication has to be done by some company. So after designing, it'll send the chip to TSMC, which is located in Taiwan. So TSMC has captured around 90% of the sorry, fabrication market. So, but in order to do fabrication, it needs a machine called lithography machine. There are two kinds of lithography machines. One is the deep lithography, and other is the extreme lithography, ultraviolet lithography machine. Now, which is the craze of, now that's the craze. So that lithography machine is manufactured by only one company in Netherlands, and that is ASML. It has complete monopoly on that. So what happens? NVIDIA designs the chips, it sends it to TSMC for fabrication, and TSMC, in order to fabricate, it has to procure that machine from ASML. It gets that machine from ASML. Okay, so ASML basically makes that machine, and after the fabrication is done, the chip needs to be assembled, tested, and packaged. Okay, so this is done in different countries. Okay, let me give an example. In the slide, if you look at the slide, there are several choke points. Okay, which are the countries which are good in designing? Say countries like US, design, core IP, and EDA, US leads. Okay, and if you go to manufacturing equipment, it's Netherlands, US, EU, and Japan. Materials, you talk about materials, semiconductor materials, China, Japan, Taiwan, and South Korea. Manufacturing, as I said, wafer fabrication, you have Taiwan, South Korea. Okay, so assembly, packaging, you have China and Taiwan. Now, NVIDIA is a fabless company. It just designed, and fabrication is done by TSMC. Sorry. There are companies which are called integrated device manufacturers. They do everything in the process. Like you have Intel, one of the oldest companies. Okay, when it comes to chips, started the entire thing in 1950s. Then you have Samsung, which is also an integrated device manufacturer. They do everything. Okay. Now this the supply chain is very important from policy perspective. Okay, in order to make effective policies when it comes to compute, understanding the semiconductor supply chain, which is very complicated, is understanding it is very important. Now, this slide is basically a graph. It talks about the companies. Say, for example, equipment, you have ASML out here, right? Design IP EDA is made by, this is not important. Equipment ASML, raw materials comes from this company is fabless. You see, fabless companies, they don't do the the fabrication thing, which is done by companies like TSMC. It's a foundry. TSMC is a foundry, you can see there. So fabless companies like NVIDIA, Broadcom, Qualcomm, AMD, okay? Assembly is done by these companies. Now, I talked about integrated device manufacturers. They do everything. They do designing. They do foundry work. They do assembly, test, packaging, everything. So we have some big names out here like Texas Instruments, Samsung, Intel, and Micron, okay? So these are the companies who are in the semiconductor supply chain, okay? Now, in the beginning, I said that this presentation is divided into three parts. First is what is compute? We understood what is compute. We talked about hardware, software, infrastructure. What is compute? Second, why? Why is compute important? Okay, because we have data algorithms. We can govern data algorithms. Why compute? Because compute has certain advantages over data and algorithms. It has disadvantages too, but it has some very important advantages. Now, I'm coming to the third part of my presentation, which talks about how. We talked about what is compute. We talked about why compute. Now we're going to talk about how we govern compute. Okay, all of us know what is governance. Now, if I had to say what is compute governance, so compute governance is a subfield of AI governance. So there are different ways you can govern AI, right? So one way of governing AI is governing compute. Okay, so compute governance is a subfield of AI governance which regulates and governs access to computational resources. I'm sorry, I'm extremely sorry. Okay, so it basically governs and regulates access to computational. We'll go to that. How do we govern compute? Okay, there are different ways. Now, before that, it's very important to understand why is it important to govern compute? Okay, see, all of us know AI systems have risks. Okay, potential risks. We need to mitigate the risks. That's why we have a unconference like this, AI safety, right? Great initiative. Okay, so governing AI compute can play a vital role in the governance of AI. Okay, as I said before, there are different ways you can govern AI. So one is governing AI compute, which is key, which is vital. Okay, now for example, what does the second point say? I've got 7 points here. Okay, I'll explain them one by one. Now, I've covered point number 1. Now, point number 2 is by governing compute, governments would be able to guide the development and deployment of AI systems in a manner that aligns with policy objectives and societal values. I'd like to give an example. October 30th, 2023. All of us know the United States government passed the Executive Order 14001. It is very important to know what's the title of this executive order. It says ensuring safe, secure, and trustworthy, okay, development and use of AI. So what are the key words out here? Safe, secure, and trustworthy. Okay. Now what happens in that executive order? It talks about it gives a computational threshold. Like if someone uses a compute threshold of which is beyond 10 to the power 26, it has to report to the government. Okay, so I am not going into the reason why they have kept 10 to the power 26, but any AI developer, AI company uses computational threshold beyond 10 to the power 26, it has to be reported. Now, what that does is, see, when you are using, I have talked about scaling laws. You use more compute, there is a possibility of developing an AI system which is more powerful, more capable. And what happens when you have a capable AI system and there is a possibility that this system can have massive risks, right? Now, what is the policy of the government? The policy says safe, secure, and trustworthy. So when someone develops uses compute beyond 10 to the power 26 and reports to the government might come in and say, hey, buddy, you're using 10 to the power 26. This can have this kind of an effect on the society. Okay. Now, what you got to do is you got to take these steps. Say, for example, you have to scale. You can scale, but you have to be responsible, right? So what this does is by knowing about this brings visibility. The government knows what is happening, and it can tell the AI system developer to make sure that the system they develop is safe. So that aligns with their policy objective of safe, secure, and trustworthy AI. That's point number two. Now, coming to point number three, we know compute resources are finite because it's finite because all of us, we talked about supply and demand. Okay, there is hardly, because demand outstrips supply when it comes to GPUs. And often they are costly. Everyone cannot afford compute, right? Now, what governing compute, what it'll do is it'll ensure that they are allocated efficiently and in a fair manner. For example, there are researchers, right? Damn good researchers who are working, but they don't have access to compute. So what government policy objective can be? The government can make a policy like, see, this is, and government has done it. So some amount of compute government can keep it for these researchers, or say not much of academia or say academia. Okay, so they can give the compute access to compute to this researchers in academia, where they can do their research, and they might come out with beneficial ways of mitigating risk of AI safety. So this can be a policy objective, fair and fair and efficient manner of allocation of compute. Okay, that's number three. Now, coming to point number four. Okay, now when the government monitors, like for example, when I said 10 to the power 26 compute threshold, you got to report to the government. What is the government doing? The government is monitoring. Okay, now by monitoring these kind of things, the government would be able to gain insight into what is happening. What is the trend as far as compute usage is concerned? Okay, what kind of compute, how much compute are companies using, what they are using for? So these are valuable insights for policy making. If you know what, say there are 10 companies, they're using compute from cloud providers, and cloud providers, government is getting information from cloud providers, right? So these kind of information, this information is valuable. The government knows what is happening inside, right? So it can help them gain insights into the trends, what is happening, and the potential risk. So what happens then is the government can take proactive measures instead of sitting back, waiting for something to happen, taking a reactive measure. Here, what happens? The government is taking proactive measures, right? Because the government can gain insights, right? So that's number four. Now, coming to number five, governments can use compute governance as a strategic tool. Now, how? See, all of us have heard about this export controls on advanced chips to China. Sorry. Now, what the government perceives, there is an apprehension that if the chips, advanced chips, okay, it can be H, whatever, 100, A, 100, whatever. So if the advanced chips are exported to China, the Chinese government might use it for military purposes. So the government is putting export controls, right? Now, what is that? It is used in a strategic manner. See, chips now, this compute thing is a global, it is a strategic, it's a national security matter now. Okay, so they can, plus that is one strategic way in which the government is using compute. Now, support local industries. Now, what is the government's policy till now? August 9, 2022, the government passed the Chips and the Science Act. Now, what is the objective of that act? The objective of that act is to invest in chips manufacturing, R&D, and workforce development in US, right? So by investing, inviting investors to invest in the American chips industry, what is the government doing? The government is supporting local industry, right? So what is happening out here? The government is using compute as a strategic way, and as a strategic tool, and in a responsible way. Okay, that's number five. Now coming to number six. Number six, AI systems become more advanced. We know with every few months we are coming out with systems which are powerful than the previous one, so they're more advanced. So We're going towards frontier AI. So as AI systems become more advanced, ensuring that they are safe is key. See the word in recent Korea summit also, the recently the American Safety Institute came out with their what are the goals, and the Commerce Secretary Gina Raimondo also talked about safety, AI safety, and why. That's why I keep on saying this unconference is timely, because safety is a big issue now. So as AI systems become more advanced, ensuring that they are safe is key. Okay, so governing compute can contribute to policy goals. So, for example, executive order. If you go back to the executive order, what is the policy goal of the government? The policy goal of the government is to ensure safe, secure, and trustworthy AI. Right? So, so what happens is when AI systems become more advanced, we have to make sure they are safe, right? So that we achieve our policy objectives. Okay. Number 6 is gone. Number 7. As the amount of compute used to train AI models has increased exponentially, we have seen that it's been increasing exponentially, not in a linear or quadratic manner, but exponentially. Hence, governing compute will help to manage this advancement in a sustainable manner. I'd like to give an example. All of us know the effect of AI on the climate, on environment. So the government can make a policy that if you use a compute threshold beyond this, blah, blah, AB, right, you got to make sure that it does not affect the environment, number one. Number two, you got to be responsible towards the environment. You have to take counter measures, like so that it does not affect the environment, right? So in this, government can be able to manage compute in a sustainable manner, and which will be very, very important for informed policy making. See, this presentation is totally about policy. To understand policy, we need to understand a basic idea about compute, right? Now, the thing is, policymaking has a big role to play. It has to be proactive. It has to be informed, right? So now going back to the next slide, sorry. Um, Going forward, I have told about, okay. Now in the beginning, I talked about governing. See, there are different ways. You can either govern data, you can govern algorithms, you can govern compute. Okay. So basically, you're governing AI in some way or the other. No, but there are advantages of governing compute vis-a-vis data and algorithms. It is very easy to govern compute compared to data and algorithms. Why? Because if you look at data, you can go to any common crawl, any site, and you can download data. It's virtual. And if you look at algorithms, you can get access to algorithms from anywhere. And it is intangible. Compute is not intangible, it's tangible. Okay, you have algorithms published in different scientific journals. You can easily get access to it, right? They are easily shareable, okay, over the internet, right? We cannot do that with you cannot easily share a chip. You cannot easily share a data center, right? Which is not possible, right? So compute is very easy to control compared to data and algorithms. Now why is it easier to govern compute? Now the thing is, number one, excludability. Restricting access to data and algorithms is difficult. As I said before, it is very easy to send data and algorithms over the internet. It can easily cross boundaries, but not like compute. For example, take the example of a chip. Okay. For example, America, by imposing export restrictions on China on advanced chips, has excluded China from getting access to those advanced chips. This is one way, one good example of excludability. You have excluded China from getting access to advanced chips. Second is quantifiability. Okay, computational hardware can be easily quantified. Like processing, the amount of processing that is taking place, you can easily quantify. Now, how do you measure that? By plots. Floating point operations per second. It can be quantified. Third, heavily concentrated supply chain. I have already talked about the supply chain. There are only few countries in the world. They make the parts. Let's see, if you divide the semiconductor supply chain into 10, one company is doing one part, another company is doing another part. Okay, one country A is good in designing, country B is good in manufacturing equipment, country 3 is, sorry, good in manufacturing, in fabrication. So it is heavily concentrated on parts are concentrated on different countries. Okay, and the chips are produced in a very complex manner. It's a very complicated process. See, without chips, nothing will work. You take a car 20, 40, 30, 40 years ago, the car was a mechanical machine, right? Now it's completely electronic. How many chips are there in the car? You look at your coffee maker machine, right? So everywhere that we need chips, right? So detectability. So you see, you can easily detect the data center, right? It's very difficult to detect who has access to an algorithm. It's very difficult to detect. Who has got access to data? It's very difficult to detect. You cannot go inside someone's house, okay, and ask him, hey, buddy, have you gotten hold of algorithms? Have you gotten hold of this amount of data? But you cannot do that. But with compute, you can easily do that, right? So that's why it's easy to govern compute, right? Next is now a few examples of compute governance. Now I'd like to give an example of compute governance. I have already said this. EO is our executive order 14110. I have been giving this example of trading runs. If you're using compute beyond 10 to the power 26, then you have to report, number one. If you're using biological sequence data, okay, and using a compute power of 10 to the more than 10 to the power 23, right, you have to report. So these are few examples of compute governance which has been initiated till now. Number two, BIS, the Bureau of Industrial and Security of the Department of Commerce, has imposed export controls. I've been talking about it on certain advanced chips to China. Third, Japan has also export restrictions, okay, on semiconductor manufacturing equipment. So there you need an export license, right? Then Netherlands imposes a national authorization requirement for the export of certain advanced semiconductor manufacturing equipment, mostly lithography machines. So these are examples of compute governance, how the government has been governing compute till far, okay, thus far. Sorry. So there are different ways of governing compute. This is what we have seen till now is directly the government is governing compute, but there are different ways of governing compute, like there are indirect methods of governing compute. Now, as the story I have been telling thus far is, not many people have access to compute. Okay, as an individual researcher, it's very difficult. Forget about researchers. There are some companies who do not have access to compute. That's why OpenAI has a partnership with Microsoft, right? So we can govern the compute. Who has access to compute? It's mostly the hyperscalers, right? The cloud provider. We have the AWS, which is leading the way, controls around 30% of the market. Then we have Microsoft, around 15 to 20% of the market. Then Google, 11 to 15% of the market. The rest 30% other cloud providers. So these three and a few others have the compute infrastructure. So as an AI developer or AI company, you have to go to those cloud providers to get access to compute, right? Now, what you can do is instead of directly governing this AI companies and developers, you can govern them through this cloud provider indirectly. Okay. Now, how compute providers can play a significant role? Now, they can be record keepers. Now, all of us go to the bank and we deal with the financial institution. And when you go to the bank or a financial institution for the first time, they do our KYC, know your customer. And this is something which is compulsory because that's their compliance thing. Because the government mandates or the regulator or whoever is the bank regulator, right, mandates that you do your KYC before opening an account, right? So while doing KYC, the bank or the financial institution has to collect a lot of information about the company, about the individual, sorry. So in the same manner, the compute providers can act as record keepers. They can collect information about the AI company or the developer who has approached them to access compute. Now, these record keeping serves three key objectives. It provides visibility into AI development. So when you are taking information, for example, various kinds of information, like what kind of compute, how much do you want, what is your use, what is the purpose, how you're going to use it. So all this kind of information, when they take it, I'm extremely sorry. It gives them visibility that about the AI company and developer, what they're going to do with the compute, right? So when the government calls for record from these AI compute providers, they can also look into lift the veil and look into what is happening inside the what is that company dealing in, okay, what they're involved in, okay. Now the second key objective, what record keeping serves, it enables compute providers to identify their customers. You know, when some AI developer or AI company is going to a compute provider, okay, and giving the information, it helps the compute provider know who that particular person is or that company is, right? So that is the second thing. And the third thing, objective that the record keeping serves, it enables post-incident attributions and forensics. Now, I'd like to give an example. For example, God forbid, something AI system is deployed, developed, and deployed, and something bad happens. If someone is hurt, something happens. Now, when you have that record keeping thing, you know who to attribute liability to. Okay, who's the person who's in charge and who should be liable for whatever harm has occurred. Right. That is number one, attribution of liability. And number two is forensics, right? So what happens is you can open the black box and see, reverse engineer and see what led to the problem so that you learn from it. You learn from the mistake and you don't commit the same mistake again. That's how it helps. Okay. It also helps. They can also be verifiers. Number two, cloud providers can also be verifiers. They can actively verify the AI companies' identities. Okay, and since they have the information, they can verify and they can see whether these companies or the developers, they are complying with the regulations or not. Now, this may include confirming identities of customers. Okay, they can confirm the identity of customers who use substantial compute resources, and they can also verify the type of computational workload run by customer, because the customer will come and say, I'm going to use this amount of workload. So now they can say, they can monitor, the compute providers can monitor and see whether they are using what they are declaring, right? Um, Whatever they have claimed. Okay, so in that way they can act as verifiers. And number three, they can act as enforcers. Okay, uh, for example, what I mean by enforcers is, I'm sorry, yeah. Now, when they are verifying the company to see whether they have complied with a certain regulation or standard or not, and if they say, if they see that a particular compute provider or AI developer has violated any kind of any kind of regulation or standard, what they can do is the compute providers can restrict or limit access to this rule-making customer. Okay, because as the customer is not relying, or sorry, not following the regulation or standard, the compute provider can restrict or limit access to this customer. Number one. Number two, they can prevent them from developing or deploying certain kinds of AI systems with that provider. And it may also limit compute resources devoted to workloads that raise red flags. So in this way, not only directly, but indirectly, governments can govern compute. Now, as I said before, this is uh, in order to make policy effective policy, it's very important to understand the work, the how the technology works. So now with the slide, I'd like to end my presentation and thank everyone for watching this, being patient and watching my presentation. I hope you liked it. Thanks a lot. And if you have any questions, you can ask.